Hi, in the previous videos, we took a look at how you can quickly get started with the robotics development kit, and we saw some frameworks that will help you create a camera pipeline and quickly deploy that AI model on the dev kit. In this video, we'll focus on ROS or the Robotics Operating System. We'll see how you can install ROS on the dev kit and how you can collect some sensor data and get some wheels moving. ROS or the Robotics Operating System is really built around helping developers create those robotics applications. So it really comes with some libraries that are custom built for deploying robots and abstracting all of those inner workings of robots. So it comes with libraries like perception, sensor processing, mapping, navigation, and much more. It also comes with libraries for communication or messaging. It's called the ROS communication layer. That really helps different subsystems within a robot to talk to each other, right? So you can get sensor data, you can pass that on to other programs. You can then also use that communication layer to move some wheels. So this open source nature of ROS has really made it really popular with developers and researchers in the robotics ecosystem. We'll take a look at how we can use different platforms, off-the-shelf platforms, for example, the TurtleBot and the MBot, and how you can integrate these platforms with the robotics development kit from Qualcomm and get some wheels moving. So I'll kick us off with a very high-level architecture of how developers can really use ROS and all the other tool chains to build their robotics applications. At the bottom layer right here is basically all the hardware connections to the dev kit. These are sensors, IMU sensors that are already on the development kit, camera compute blocks that are getting camera data from the ISP and then making them available to the application using the IM SDK or the GStreamer plugins. For the sensor data especially is also abstracted to the application layer using ROS. So the IMU sensors on the dev kit is available to developers using a ROS node, right? So we'll take a look at some steps of how you can actually get this data. And then once you have the ROS node data of the IMU sensors, once you have the camera data, you can integrate all of these different aspects of within your robotics application using GStreamer plugins, right? You can daisy chain output and input from one particular element to the next element, and you can feed it to the ROS node. You can take output from the ROS node, feed it to your application based on your what your use cases are. So let's get into it. We have Ramya who will walk us through installing ROS and give us an introduction on TurtleBot and how you can integrate Qualcomm Robotics RB5 development kit with TurtleBot and use ROS to move the wheels.
Hi everyone, I'm Ramya. I'm an engineer from Qualcomm. Since you have just seen an introduction to ROS, let's now see how to install ROS on the Robotics RB5 development kit. Here I'm using the development kit with one of the latest releases. You can check out our documentation to find more information related to our latest releases. There are 3 ways to access the DevKit shell: using ADB platform tools, using SSH, and using the DevKit as a standalone PC by connecting a monitor, keyboard, and a mouse. For this video, I will be using the ADB method. Let's now take a look at the ROS installation steps at a high level. Once the DevKit is powered on, connect a USB-C cable between the DevKit and the host PC and enter the commands as seen here to log in as the root, remount the file system with the read-write access, and access the DevKit shell. Once you are in the DevKit shell, the first step for ROS installation is updating the system packages and installing locales. Once locales is installed, we have to set up the locales, which means setting the environment variables to define the language, region, etc. in the Linux interface. The next step is to add ROS repository to the DevKit. Ensure Ubuntu Universe repository is enabled using the commands as seen here. Update the system packages and install curl. Using curl, download the ROS key as seen in the video. Add the ROS repository to the sources list so the development kit can accept software packages from ROS. Update and upgrade the system packages and install ROS. This video uses ROS Foxy, but you can use any version of ROS supported by the Linux version on the development kit. ROS installation could take anywhere between 15 to 25 minutes. Once ROS installation is done, the next step is to add the required environment variables to the bashrc file and then source the bashrc. This completes the installation and setup of ROS. Now let's move on to the next steps. Let's test the ROS setup by running a simple talker and listener app using ROS nodes. Open another command prompt window, log into the devkit shell and source the bashrc file so the environment variables are set in the new terminal. You have terminal 1 on the left and terminal 2 on the right. Run the talker node in terminal 1 and listener in terminal 2. You can see that the two nodes are communicating. You now have ROS up and running. Now that you have ROS running successfully, let us run an app to get the IMU sensor data from the development kit. You can follow the instructions from ROS IMU sample app to set up the ROS node. In terminal 1, run the IMU ROS node. In terminal 2, run the command as shown to see the IMU data being published. You can see the IMU data changing as the development kit is moving. So far, we have seen how to bring up ROS and how to access sensor data using ROS nodes. Now, let us move on to our first moving base, the TurtleBot 3. The TurtleBot 3 is an open source mobile robot that works with ROS. It comes with Dynamixel actuators that are connected to the OpenCR board. The OpenCR board is serving as the motor control board and it drives the Dynamixels to move the TurtleBot. The OpenCR board powers up the development kit. We have a USB hub connected to the development kit. There are three components connected to the USB hub: the LiDAR sensor, the USB camera, and the OpenCR board communicates to the development kit via the USB. Now let's move on to the software setup of the TurtleBot. For the first part of the software setup on TurtleBot, let us download and build the necessary packages. Install the required Python packages like rcomplete, Qualcomm common extensions, etc. as shown here. Create a new directory and git clone the TurtleBot repositories and drivers. Let's take a look at the repositories cloned. Use Qualcomm, a command line tool, to build all the TurtleBot packages. This step will generate 3 additional directories, namely build, install, and log, as seen here. Now set the environment variables such as TurtleBot 3 model, LiDAR model, etc. and source the bashrc file. Let's proceed to the second part of the software setup on TurtleBot, which is setting up the OpenCR board. Create a new directory to place the OpenCR firmware and download the latest firmware. Extract the downloaded tar file. Set the environment variables like OpenCR model and OpenCR port. Add ARM-HF packages using dpkg as OpenCR is a 32-bit microcontroller. Update the system packages and install the standard C library for ARM-HF. Navigate to the OpenCR update directory and run the update script by passing the environment variables set earlier. You should see the terminal logs as here once you start updating the firmware. OpenCR plays a chime indicating the firmware update is done. At this point, the TurtleBot is completely set up. You can run a simple test to ensure the successful setup. Press and hold down the switch 1 on OpenCR for a few seconds to command the robot to move forward for about 12 inches. Now that you have run a simple test on the TurtleBot, let's get the TurtleBot moving around. I have two command prompt windows here serving as two terminals of the development kit. Log into the dev-kit shell and source the bash rc file to set the environment variables. In the terminal 1, run the TurtleBot bring up launch file. This makes sure that all the components like the dynamic cells, OpenCR, LiDAR, and the USB camera are communicating with the development kit. In the terminal 2, enter the ROS command to move the TurtleBot left. The X, Y, and Z values in the linear and angular parameters are used to determine the speed and direction of the TurtleBot. We can see the TurtleBot moving left. Let's move the TurtleBot to the right. Let's move the TurtleBot forward. Let's move the TurtleBot back. Let's stop the TurtleBot. Hit Ctrl+C to end the application. Hope you enjoyed learning the bring up and the working of TurtleBot 3. In the next video, let's see another moving base, the MBot. And for this, we'll have Rahul joining us. Take it away, Rahul.
Thanks, Ramya, for walking us through the TurtleBot installation and getting the wheels moving. Hi, everyone. My name's Rahul, and I'm an engineer at Qualcomm. In this section, we'll be integrating the RB5 dev kit with the MakeBlock MBot kit. By the end, you'll have an MBot with an RB5 on top that can be driven around with a controller or joystick. Let's get started. Once you've assembled the MBot by following the instructions in the kit, you'll want to connect the MegaPi controller board to your computer using a USB cable. The plug is located on the side of the robot here. After the controller board is connected to the computer via USB, we can set up the software. First, we'll navigate to the Arduino homepage, which I have here. Then click on the Software tab. In this case, I'm on a Windows machine, so I'll click on the MSI installer and let it download. We also need to go to the MakeBlock Libraries repo on GitHub. We click on Code, then Download Zip. Now, once the Arduino installer finishes downloading, you can run it to install the Arduino IDE. I already have it installed, so I'll skip this step. Instead, I'll go directly to the Arduino IDE like when you first run it. I'll navigate to Sketch, then Include Library, and Add Zip Library. It'll ask me for the file to open, so I'll go to the directory that I downloaded everything to and open the MakeBlock Libraries file. In the corner, we can see that it is processing. Once it's done, it tells me in the output section. Next, we go to File, Examples, MakeBlock Drive, Firmware for MegaPi. This will open in a new window. Once it finishes loading, we set the board by going to Tools, Board, Arduino AVR Boards, Arduino Mega 2560. Then we select the port that the MBot is connected to the computer with Tools, Port, COM4. In my case, it's COM4, but yours might be a different number. Finally, I press Upload to compile the firmware and write it to the board. Once it finishes, we're done with this section. Now we'll attach the RB5 board to the MBot. In my case, I've 3D printed a small bracket to put the two together, but just zip ties are sufficient as well. Once you've done that, you can connect a battery using the DC barrel jacks on the RB5 and the MBot. Finally, you'll need to connect the RB5 to the MegaPi board under the MBot via USB. Now we can start setting up the software on the RB5. The steps that I'm going to show you will apply to the LU 1.0 build and kernel version 4.19.125. First, I'll run the uname-r command to give us the current running kernel version. You can see that it's 4.19.125. Next, I'm going to use the wget command to download the source code for Linux kernel 4.19.125, the version that we're currently running. Once that's done, we can run ls and see that there's a tar.gz file. We can extract this file using the tar command. Once that's done, we have a new directory, linux-4.19.125. This has the source code for the kernel. We also want to make our own directory called joydev. We then copy some files from the Linux source code directory into the new joydev directory. Then we can cd into the joydev directory. At the start, we can see a bunch of C source code files and a makefile. We need to edit the makefile, so I'll use the vi command, but you can use any text editor. We just copy some lines to the bottom of the file. Finally, save and quit, and run make to build the code. Once it's done, we can run ls and see that we have a new file, joydev.ko, which means it was successful. We'll run insmod joydev.ko to load this new module into the kernel. Next, we'll move back one directory and create a script called joydev.sh. This script will set up the joydev kernel module to be automatically loaded. Finally, I'll run the script using bash. It says joydev loaded, which means it was successful and that we're done. Now that we've set up the joydev kernel module, we'll go through a very similar set of steps to install the ch341 kernel module. Again, I'll run uname-r to give us the current kernel version. In this case, it's 4.19.125. Then again, I'll download the source code for the Linux kernel that matches the current running version. Once that's done, we'll again run ls and see that there's a tar.gz file. We can extract this file using the tar command. Once that's done, we have a new directory, linux-4.19.125. This has the source code for the kernel. We'll also make our own directory, ch341. Then again, we'll copy some files from the Linux source code directory into the ch341 directory. And after that, we can cd into the new directory. At the start, we can see a bunch of C source code files and a makefile. We'll need to edit the makefile, so again, I'll use the vi command. We just copy some lines to the bottom of the file. We'll save and quit, then run make to build the code. Once it's done, we'll run ls, and we see that we have a new file, ch341.ko, which means it was successful. We can run insmod ch341.ko to load this new module into the kernel. Next, we'll move back one directory and create a script called ch341.sh. This script will set up the ch341 kernel module to be automatically loaded. Then I'll run the script using bash. It says ch341 loaded, which means that it was successful and that we're done with this section. In this video, I'm going to test the joystick. We start by sourcing the ROS setup script, as we've seen before. Once that's done, we'll start the joy node using the command ros2 run joy _node. It gives us some feedback that we opened a joystick, which is good. We then switch to another terminal window. Again, I'll source the ROS workspace. Once that's done, I'll run the command ros2 topic echo /joy to print the output from the joy node that we just started. The text scrolls by very fast, so it's hard to tell, but there is a change when I press buttons and move the axes on the joystick in the output here. At this point, it might also be useful to figure out which axes and buttons in the software correspond to the physical buttons and joysticks on the controller, since you'll need that later. You can do that by just pressing a button and seeing which output changes. At this point in our guide, we have a working controller, so it's time to get the robot moving. I'll start by installing the MegaPy library for Python using pip. You can see that I already have it installed. Ideally, you would install into a Python virtual environment, but I'll skip that for now to make it simpler. Then, I'll source the ROS setup script as we're used to by now. Once that's done, we'll create a new directory to work in and cd into it. I'll then clone a Git repo using the git clone command. Once you're ready to build the program, you'll want to cd back to the RB5_WS directory that we made earlier and run the build command build --paths source /RB5_ROS2 /RB5_ROS_control. After that finishes, you can run the command source install /setup.bash. And once that's done, you'll want to switch to another terminal window and start the joy node like we did earlier when we tested the joystick. Then we switch back to the original window and run the command ros2 run RB5_control RB5_MPI_control.py, and we can tab complete this, which is nice. We get some output, which is good, so now we'll want to move the joysticks and see the robot move. Now that we've started up the program, we'll be able to move the robot using the controller. I'll press a button on the controller to indicate that I want the robot to move. Then I'll move a joystick and observe that the robot does move. If yours doesn't move, or doesn't seem to move in the right directions, it's likely that your controller has a different button mapping, or that the motors on your robot are wired in a different order. These are both easy problems to solve with just software.
So to recap, in this video, we gave you a brief introduction on ROS. We showed you how to install ROS on the Qualcomm Robotics RB5 development kit and how you can use ROS to collect some sensor data using ROS nodes. We also had Ramya walk you through the TurtleBot 3 setup, how you can install TurtleBot 3 packages on the dev kit, and how you can use the dev kit and ROS to control the robot. We also had Rahul walk you through similar steps on the MBot dev kit and how you can use RB5 development kit to control MBot robot. So stay tuned for more information. Click the link in description for more content.